So now we have to think about what happens when we are inside of this shell. So we might try to figure out the electric field at this point. So we draw another sphere. So again, my pictures are not symmetrical. Your pictures are better because they're coming out more symmetrically.
And then E should be constant there also.
Yeah. So again, this is going to really come down to just being E times A.
And A is for pi little r squared again.
Yeah, you still find the area of this smaller sphere the same way as before.
But now Q enclosed is Q again?
Yeah, it is Q. That's right.
And that's
Now, notice now that we're disregarding this charge over here, because this charge is not enclosed. The only charge that's enclosed within this, this Gaussian surface is the positive Q. So we just have this Q, and we're disregarding this Q over here, because it's not enclosed. Good. So that gives us this formula. So what's the answer to the question?
it's the same at any point, I guess, at all points in space. It's Q over 0.4 pi r squared E naught, or E0. Is that fair?
That was a good answer, but that would only be half credit. Because
Oh, actually I take that back, because outside, when r is greater than big R, they're pointing towards the sphere,
Right.
the spherical shell.
right.
And when little r is less than big R, they're pointing away or out.
Okay, good,
So
good.
then it seems like it would be 0.
I'm sorry?
It seems like it would be 0 overall, right?
Well,
No.
there is no overall. There is just what's the electric field at any particular point in space.
okay.
The electric field at one point doesn't get added to the electric field at another point. Those are just
I
separate
see.
points. I think you might be thinking about the electric flux.
Uh-huh.
And we talked about how the electric flux that comes in one surface can cancel the electric flux on another face.
Okay.
So electric flux is considered a global concept. The electric flux is calculated over the entire surface. So
Yeah.
the flux from one face of the surface can cancel the flux from another face. But the electric field is a local concept. It just is the electric field calculated at a point in space. So there's no reason to add these two things together unless they're at the same point in space. So is the electric field a vector or a scalar?
It's a vector.
We reviewed that at the beginning.
Yeah.
And one reason why you need to know that is that means if they ask you for the electric field, you haven't given a full answer unless you've given both the magnitude and the direction. And the part that you were originally forgetting was to give the direction as well. All right, now to be honest, your instructor probably is a nicer guy than me. He would probably say, find the magnitude and direction of E at all points in space. But even then, a lot of times people forget that they need the direction as well.
Yeah.
All right, so to draw the electric field vectors here, when we are at this point, the enclosed charge is negative, because negative Q, negative 2Q plus positive Q is negative Q. Well, electric field vectors we know point towards negative charges. So when we're on the outside of the hollow sphere, just like you described, the electric field vectors look like this. However, when we're on the inside, the enclosed charge is positive, and we know that electric field vectors point away from positive charges. This I'm just repeating what you already correctly said. So basically, the formula for the magnitude of the electric field is the same everywhere. However, the directions are quite different in different places. This would have been easier to remember if we'd kept in the signs. If we'd kept in the signs, this would have had a negative sign and this would have a positive sign. But that doesn't really tell you the direction of the electric field directly. So I think it's better just to separate the magnitude and the direction. The formulas for the magnitude turned out to be the same in both cases here, but the directions would have been quite different. So notice that the direction of the electric field, again, when we're working with spherical symmetry, the direction of the electric field only depends on the enclosed charge, not the charge that's outside your Gaussian surface. When the enclosed charge is positive, the electric field lines are pointing away from it, and when the enclosed net charge is negative, the electric field lines are pointing towards it. I just want to point out again that we didn't necessarily have to do all this work of drawing Gaussian surfaces. We could have just looked up these formulas. What would happen if we just looked up these formulas in your handout? Well, if you use your handout, I guess we would use spherical symmetry. And I guess we would use this formula for when we're outside of a sphere. So if you look at the handout, when you're outside of spherical symmetry, here's the formula from the handout. And the key is you can use this formula anytime you have charges that are spherically symmetrically distributed, as long as you only plug in for Q the enclosed charge. So when we're out here, the enclosed charge would be negative Q, and we would just plug that into this formula and get this. And when we're over here, the enclosed charge would be positive Q, and we would plug that into this formula and get this. So you could have taken a shortcut and just gone straight to this formula. But I think at this point in the course, the instructor wants you to know how to do it this way as well. Maybe you get a little more credit for that on the exam problems. Once again, we have to be very clear about the difference between little r and big R. Okay, well, I guess that's about all the time we have for this. So what is it that we didn't get to talk about here yet? Well, we talked about one type of symmetry. There's two other types of symmetry. There's line symmetry and plane symmetry. Now, spherical symmetry appears much more often on exams than the other two types, so we ended up spending all our time on that. On the homework, you'll probably see all three. There are examples in the textbook that show how to do the Gauss's law for line symmetry and for plane symmetry as well. And there's also formulas for those. Those are in the handout. Maybe in the future we'll get a chance to go over them at some time. Even though spherical symmetry comes up more often on the tests, you might see that the plane symmetry and the line symmetry too. All of them are important. But this is the most important, so this is what we ended up spending our time on.